If you're looking into AI agents but aren't fully convinced, you're not alone. They're usually presented as a black box. There's plenty of hype but very little clarity on how they actually work or where they truly make sense in a business. That lack of clarity is what makes them feel risky. AI agents aren't autonomous entities. They are systems. Systems composed of reasoning, tools, memory, and control logic. So in this video, I'll walk you through that system and give you a clear mental model so you can understand how an agent actually operates and when it makes sense to use one in your business. If you're new here, I'm Fraser Dorado, and I've spent nearly a decade building large-scale enterprise systems, and today, through my AI and automation agency, I help teams design scalable, reliable AI systems. Everything I show you here comes from building the systems and deploying them in real-world environments. What I've seen consistently is this. Most hesitation around AI agents doesn't come from the fear of AI. It comes from uncertainty. When agents are introduced, they're often framed as autonomous, self-directing, or intelligent systems that just figure things out. But there's rarely any discussion of control, constraints, or failure mode. So we are left with this gap. On one side, you see these impressive demos. On the other, you're responsible for systems that need to be reliable, observable, and predictable. That mismatch is where we start to lose trust. Because when you don't understand what's actually making decisions, what the system has access to, and how it behaves when something goes wrong, you're no longer evaluating software, you're gambling on behavior. The real issue isn't that AI agents are not trustworthy, it's that they are often presented without an architectural explanation. And in engineering, trust doesn't come from belief, it comes from constraints, visibility, and control. So let's start there. How to think about agents as systems, not as products, not as demos, and definitely not as autonomous entities. We are going to look at AI agents the same way we'd evaluate any other system, by breaking them down into components, understanding how decisions are made, and identifying where control actually lives. I'll start by giving you a simple mental model for what an AI agent really is. Then we'll look at the core components that make an agent work as a system. From there, we'll have an honest conversation about where agents work well, where they fail, and why human in the loop isn't optional in many real-world cases. And finally, I'll explain why patterns like React exist, as a way to reduce ungrounded reasoning by forcing a tight reason, act, observe loop. By the end, you won't just have a better definition of an AI agent, you'll have a way to evaluate them, the same way you would evaluate any other piece of software. And the foundation for that evaluation is a simple mental model. At a system level, an AI agent isn't mysterious at all. An AI agent is a software system that repeatedly observes its environment, decides what to do next, takes an action, and then evaluates the result. That's it. There's no autonomy in the human sense, there's no intent, there's no goal-seeking intelligence running in the background. What you actually have is a decision loop. Each cycle looks something like this. Take in context, reason about the next step, perform an action, observe what changed, and repeat. The agent part simply means the system is allowed to take actions between reasoning steps, instead of returning a single response and stopping. Once you see it this way, agents stop feeling like a black box and start looking like something much more familiar, closer to a traditional control loop where a language model handles the reasoning and the rest of the system decides what's allowed to happen next. And whether the system is trustworthy has very little to do with how impressive the model is, and everything to do with how the loop is designed and constrained. Every production-grade AI agent is built from few core components, and each one has a very specific role. First, there's the language model. This is the reasoning engine. It interprets context, weighs the options, and decides what might be the next best step. But it doesn't execute anything on its own. For that, it has tools. Tools are how an agent interacts with the outside world: APIs, databases, internal services, and workflows. They define what the agent is capable of doing, not what it should do or when. And then there's memory. This is how state is preserved across steps. Previous actions, observations, partial progress, or constraints that need to persist over time. Without memory, there's no loop, just isolated calls that can't learn from their own actions. And sitting above all of this is the orchestrator. This is the part most people overlook. The orchestrator controls the loop. When the model is called, what context it receives, which tools it's allowed to use, and when the system stops. This is where guardrails live: rate limits, permissions, filters, and human approval gates. The model proposes actions, but the orchestrator decides whether they happen. That distinction is critical because in real systems, reliability doesn't come from smarter reasoning, it comes from clear boundaries between what can think and what can act. Once you understand the components and the capabilities, the limits of agents become much clearer. AI agents work best in environments that are well-defined, partially observable, and tolerant of iteration. They're effective when tasks can be broken down into steps, actions have clear outcomes, and mistakes are recoverable. For example, internal workflows, data enrichment, and controlled operational tasks. Where agents struggle is in environments that are ambiguous, high stakes, or poorly constrained. If success depends on deep domain knowledge, unspoken context, or irreversible decisions, agents become unreliable very quickly. And this is where human-in-the-loop stops being optional. Any system that can modify production data, affect customers, or trigger irreversible actions needs explicit checkpoints where humans can review, approve, or override what the agent proposes. Not because agents are bad, but because you should only trust a system that can fail safely. When used correctly, agents reduce cognitive load. Used incorrectly, they amplify risk. The difference almost always comes down to how the system is designed. That brings us to one of the most common patterns used in AI agent systems today: React. React is short for reasoning and acting, and it's a loop that structures decisions one step at a time. Reason, action, observation, repeat. In practice, this means the system alternates between reasoning about what to do next, taking a specific action, observing the result, and then reasoning again with the new information. What matters isn't the name, it's what the pattern solves: ungrounded reasoning. Without a pattern like React, models tend to reason in isolation for too long, without incorporating real feedback. Gaps get filled with assumptions, and errors compound silently across steps. React breaks that pattern. By requiring interaction between decisions, the model is repeatedly grounded in reality. It can check instead of assume, adapt instead of committing early, and correct course before errors cascade. This is why React shows up in so many practical agent systems today. Not because it guarantees correctness, it doesn't, but because it reduces hallucinations and compounding errors by tying each decision to an observation. React doesn't change what the model is capable of. It keeps the model's reasoning grounded in the environment, which is exactly what you want in a multi-step system. To make this more concrete, let's look at a code example. Don't worry, I'm not going to deep dive into the implementation details. The goal is simply to show you the structure, where the reasoning happens, where actions are taken, and where control actually lives in the system. Before we dive into code, let's quickly walk through a sequence diagram to understand what happens behind the scene. As you can see here, you have the user, you have the React agent, the LLM, and the weather API tool. Here the user asks a question, and the question in this case is, what's the weather in New York and what should I wear? So the React agent receives this question and it starts the loop. It takes the instructions, the tools, and the user question and then passes it to the LLM. Now the LLM has to decide what the next step is. So it thinks about this for a bit and it decides that it needs to make a tool call. So as you can see here, the action is use the weather tool. This is then passed back to the React agent. The React agent realizes that there's an action to be taken and it needs to make a tool call on behalf of the LLM. So it calls the getWeather tool on behalf of the LLM with the arguments it provides. It waits for a response from the weather API. It gets a response. As you can see here, the temperature is 5 degrees and the condition is windy. And this response is then received by the React agent. Now the React agent, which is also the orchestrator, it adds this observation to the context and then passes the whole context back to the LLM. Now the LLM will take this entire context, check the question that was asked by the user, the steps taken in between, and then realize that it has all the information it needs to come up with a final answer. And as you can see here, it does come up with a final answer, that it's 5 degrees windy and the advice is to wear a jacket. And then it passes this answer back to the React agent. Now the React agent realizes that there is a final answer from the LLM and it can end the loop. And then it passes this information, as you can see here, back to the user. That's pretty much it. And now let's quickly skim through the code and check the output. As you can see here, we have the React template. And what this prompt basically says is that answer the following questions the best you can. And you have the following tools, so where we put in the whole tool manifest. We also give it a format in the way it should think. So question, thought, action, and observation. And then we put in the input and we put a little agent scratchpad where we append the observation. We then have a call tool function which the React agent or the orchestrator uses to call the tool on behalf of the LLM. We have the execute React agent. So this is where the main loop lies. As you can see, we have the agent sketchpad. And here we have the iteration or the main loop that goes up to 10 turns. We then populate the prompt with the inputs. We generate the message and we make a call to the LLM. The LLM then gives us a response, which we check for the final answer. So if the final answer exists in the LLM response, we provide that back to the user. If it does not exist in it, then we check for any actions available. If an action is available, we make the call on behalf of the LLM, and we take that observation and then we append it to the agent sketchpad, and we put that sketchpad back in the prompt and feed it to the LLM. This loop continues till we find the final answer or the number of turns runs out. And then we created a weather assistant. So it has a very basic system prompt where it says you're a helpful weather assistant whose goal is to answer questions about weather, conditions, and forecasts. We created some simple tools, in this case get weather, in this case get current weather, and get the weather forecast. The data here is mock because I just wanted to show you how this works. And then we have a function to generate the tool manifest. It takes the tool name and the tool description, which is then fed to the LLM so that it understands how to make a tool call or what is required to make a tool call. And then we have the run agent, which actually executes the React agent. And lastly, we have the main function where we put it all together. So now let's execute this and check out the output. So we ran the code and this is what you get. I basically asked the question, what's the weather like in New York? As you can see here, the React agent started and it has the question, it has the available tools, and it populates the React prompt. So you can see the tool manifest here, the tool names, and the user question. And then it begins the first iteration. In the first iteration, you can see that the LLM thought about what it received and realizes that it needs to take an action. As you can see here, the action is called get current weather. This is the input for the tool call. So the city is New York, and the response from that is that the temperature is 22 degrees Celsius and the humidity is 65%. Now this observation is then populated back into the React prompt. So this is the same React prompt, has a tool manifest, it has the tool names, and at the bottom in the agent sketchpad, we append the observation. And then you go into iteration 2, where now the LLM has the entire context and realizes that it has enough information to actually answer the user's question. And then it comes up with the final answer, as you can see here, where the current weather in New York is partially cloudy with a temperature of 22 degrees Celsius and the humidity is 65%. That entire loop is your React agent. At this point, the pattern should be clear. AI agents aren't autonomous entities you either trust or don't. They're software systems built from components, governed by control loop and constrained by design choices. And when agents feel risky, it's rarely because the model is unpredictable, it's because the system around it is underspecified. Once you break an agent down like we just did, trust no longer feels abstract. It becomes something you can design for. That's the lens you should use when evaluating agents for your business or your next project. Not can this model do it, but rather does the system fail in ways we can tolerate. If this video helped bring clarity to how AI agents actually work and gave you a mental model to reason about them, you'll find more deep dives like this here. Hit subscribe so you don't miss the next one.